Hello everyone, I am Miss Hu, your physics teacher. In this video, we're going to be learning about thin lenses, where we will learn about converging lens, also known as convex lens, as well as diverging lens, also known as concave lens, in terms of the components and names, ray diagrams, image characteristics, as well as the uses and applications. Now, before we get started on the lesson, just a reminder to subscribe to my YouTube channel for more physics lessons from your physics teacher, Miss Hu. So now, let's get started. So first, we're going to be learning about converging lens. Now, there are a few types of converging lens, as you can see from this slide. Now, there are many different types of converging lens, and another name for converging lens is a convex lens. So converging lenses or convex lenses are lenses where the curvature is outwards, where it bulges in the middle of the lens, as you can see. A convex lens generally is a lens that curves on both sides of the lens. Sometimes the curvature could be equal and sometimes they might not be. A convex lens is just a general name given to a lens that's curved on both sides. Now, if the curvature on both sides of the lens is equal, it's known as a biconvex lens, like this. That means it's a symmetrical lens. The curvature is equal on both sides. A planar convex lens is a lens which curves outwards on one side only, and the other side is flat or plane. A positive meniscus lens would be curved on both sides, and they seem to curve in the same direction like this. So why is this classified as a converging lens? It's because for a positive meniscus lens, the light rays that travel through this lens will still converge. So you can see that the way the curvature is, the light ray will be forced to converge when they pass through this lens. Now, what makes all of these converging lenses is that all of them will converge the light rays to a single point. So on this diagram, this lens is representing a converging lens, while these lines are representing the light rays. So if we have parallel light rays traveling towards the lens, in this case from left to right, when they pass through the lens, you'll find that all these light rays will converge towards a single point like so. Of course, the light rays will then continue to travel. The main thing here is that all of the light rays will converge or focus at one point. This point, normally labeled with a capital F, is called the principal focus, also known as the focus point, also known as a focal point. Yes, all of these terms mean the same thing. So all the lenses we saw on the previous slide, all of them will cause the light rays to converge at a single focus point like this. The difference is just that the focus point may be at different positions away from the lens. So converging lenses will converge the light rays. Now for this video, we're going to focus on a very basic converging lens, meaning we're going to focus on the simplest lens to understand, the biconvex lens. So for a biconvex lens, because the curvature is equal on both sides, this means that not only will the light rays converge this way, if light rays were to come in from the other way, for example like this, parallel light rays coming in from right to left, the light rays will also converge on the other side of the lens, meaning there'll be another principal focus or focus point or focal point on this side. So for a biconvex lens, there will be two principal foci of two focus points, one on either side. Because a biconvex lens has equal curvature on both sides of the lens, therefore the distance of these principal foci or focus points is equal from the lens. So let's go through the terms that you need to know in terms of the lens. As you already know, this capital F is known as the focal point or focus point or principal focus. The measurement of the distance of F from the lens is known as the focal length or focus length. This is normally ascribed with the small letter f. So similar to the point, focal length or focus length can be used interchangeably. They both mean the same thing. Now you must take note that the measurement of the length is not from the surface of the lens, but rather from the center of the lens, as you can see from this diagram. So as mentioned, for a biconvex lens, the value of the focal lengths on both sides will be equal. So the value of the focal length or focus length for a convex lens is said to be positive because the light rays converge forward. That means the focal point is in front of the lens. That's why the value of the focal length or focus length is positive. The center of the lens is known as the optical center. The imaginary line that connects the focal points to the optical center is known as the principal axis. Next, we're going to look at how the light rays would behave when they travel through the convex lens. Obviously, they're going to refract, whether the lens is made out of plastic or glass. However, if we were to randomly point the light rays at weird angles towards the lens, it's quite hard to predict where they're going to refract. So if you're studying SPM or IGCSE, you need to learn about 3 specific light rays and how they travel. Why we learn these 3 is because these 3 light ray paths are very easy to replicate and we can determine the exact path they're going to travel through. So the first path you need to learn about is a light ray that travels parallel to the principal axis. As we had seen in the previous slides, we know that any light rays that are traveling parallel to the principal axis will always converge towards the focal point. So if we were to take a single light ray, it's still going to pass through the focus point or the principal focus. By the way, before we move on, just to point out to you, you must always draw the arrows before and after to show which are the incident rays and which are the refracted rays. That means you need to show where the light rays are coming from and where they're traveling to. So if this light ray path makes sense, then it should also make sense that if you were to get the light ray to travel in the opposite way, that means through the focal point, then what happens is that the light ray will come out parallel to the principal axis. That means that it just reverses this path. However, we're going to draw it from the left side. That means now we're going to learn about the second ray path. So if the light ray travels through the principal focus or focus point, when it reaches the center of the lens, it's going to refract in such a way that it will come out parallel to the principal axis. So as you can see, these 2 light rays are just opposites of each other. The third light ray is the easiest to understand. Any light ray that travels to the optical center of the lens will not change direction. It will continue in the exact same direction along the same ray path. So these are the 3 ray paths that you need to know. We only focus on these 3 paths because, like I said, they're very easy to replicate and very easy to predict exactly where they're going to travel to. Remember, if you point a random light ray towards the lens, it's very hard to predict in which direction they're going to refract. So for this, I'm going to label the ray paths as number 1, which is the light ray path that travels parallel to principal axis and then goes through F. The second light ray is the one that goes through F and comes out parallel to the principal axis. And number 3 is for the light ray that travels through the optical center. So next we're going to learn to draw the ray diagrams. If you don't know what the ray diagram is, I'll explain this on the next slide. But before we go into that, just to explain to you, whenever you want to draw the ray diagrams, you need to draw at least 2 ray paths. Now there's a choice of 3 here. If you wanted to, you can draw all 3. But if you just want to get straight to the answer, you only need to draw 2. And my recommendation is to draw ray paths number 1 and number 3 only. What about number 2? It is not that you can't draw number 2. However, drawing ray path number 2 will be quite confusing and sometimes it's very hard to get the answer. Number 1 and number 3 will help you get the answer for the ray diagram most easily. I'll show you this in the next few slides. One thing that I must point out to you is that when you draw the light rays to the converging lens, you must always draw the incident ray, that means a light ray that's coming from the source, all the way to the center of the lens. You only draw the refracted ray at the end of the incident ray after it has reached the center of the lens. Now this is true regardless of whichever ray that you draw, especially for rays number 1 and number 2. For number 3, it's just a straight line through the optical center. I have students who have asked, shouldn't the light rays be refracting when they reach the surface of the lens? So if we look at how we draw number 1, 2, and 3, there appears to be no refraction when the light ray is traveling from air to glass. It's a straight line through until it reaches the center of the lens. To answer your question, yes, it's true. The light rays should be refracting when they're traveling from air to glass and then from glass to air. However, after a lot of observation done with convex lenses, they found that the overall ray paths appear to follow this pattern. So as such, to simplify it for students, instead of drawing refracted rays from air to glass to air, students just need to learn an overview of the overall ray path patterns. So even though there's refraction on both surfaces in this case, generally the light rays appear to follow this path. So a light ray that travels parallel to principal axis will refract through the principal focus or focus point. A light ray that goes through the principal focus or focus point will refract out parallel to the principal axis, while a light ray that appears to travel through the optical center will continue on a straight path. So to simplify it for you, just follow these three guidelines. Don't worry about all these additional refractions because these are the overall ray paths that have found to be true for how the light ray behaves. So regardless of whatever lines that you draw, always draw to the center of the lens. The center of the lens that I am referring to is this dotted line, which marks the center of this lens. The way we draw these ray paths to the center of the lens is true for converging lens as well as for diverging lenses. So for all the ray diagrams, which we will be observing in the upcoming slides, whether for converging or diverging lenses, we will draw the ray paths to the center of this lens. That means this dotted line. So first of all, let's look at a situation where the object is placed very far away. So when we say the object is very far away, we normally say it's at infinity. Infinity in mathematics, yes, does mean a limitless number. But in the case of lenses, it just means that the distance of the object from the lens is so far away, instead of putting a number to it, we just say at infinity. So when the light rays are at infinity, normally it means that the light rays that come from the object, by the time they reach the lens, are almost parallel. So the difference in the directions are so negligible, we just draw them parallel. And as we already know, the light rays that come in parallel to the principal axis will always converge at F. So this means that the image is formed at F. If you're looking at this diagram, you might be wondering, there's no image here, the light rays are just converged. Let's look at another situation. So sometimes it is possible that the object is placed at an odd position, that the light rays are coming in parallel, and this time the light rays are not parallel to the principal axis. Remember that regardless of however the light rays come in, if they are parallel when they reach the convex lens, the light rays will always converge at the principal focus. Now, as you can see though, the light ray cannot converge at F because the light ray that travels through the optical center continues along a straight path. So what we mean in this case by converging at F is that the converging point is in line with F. Even if you have another light ray that is parallel this way, it's going to converge at a point that is aligned with F like this. So this is where the image would be formed. So this arrow over here is representing the image formed. So the difference here between object and image is this. The object is the original thing, while the image is what we are seeing through the lens. When I say image characteristics, I'm referring to the comparison of the image to the original object. Whenever we want to state the image characteristics, there are three categories of characteristics. You need to state the type, direction, and size. So these image characteristics that you state are comparing the image to the original object. So let's start first with type. There are two types of images. There's either real or virtual. So what is the difference? Let's look at this slide. So a real image is an image that can be projected on a screen. For example, if you were to use a projector, the projector will project the image onto the screen like you can see on this image. So this is the original object, meaning the computer or the slide, or if you're really old-fashioned, it's a picture slide that you put into the slide projector. What the projector displays on the screen here, this is the image. A real image here means that you can get a second copy of this projection that's different from the original object. So that's a real image. A virtual image, on the other hand, cannot be projected on a screen. That means you can see the image, but somehow, try as you might, you cannot get that second copy to appear on that screen. To understand this more clearly, I'll show you on the ray diagrams in the upcoming slides. For now, let's learn about the rest of the image characteristics. Besides type, there's also direction. So the two types of direction that you need to be able to state are upright or inverted. Upright means that the image is the right side up. So if the object has its head on top, the image that's upright will also have its head on top. An inverted image is an image that is upside down. For the size, you can have a magnified image, which means that it's a bigger or enlarged image, an image that's the same size, or a diminished image. Diminished means smaller. By the way, if you don't want to use the term magnified or diminished, you can use terms like bigger or enlarged or smaller. So now that you know about the image characteristics, let's come back to this slide and understand the image characteristics here. In this case, it's quite hard to compare because you cannot see the object. But by looking at how the light rays can travel, you should be able to see that yes, the image is formed on the other side. So imagine that the light rays are coming here and causing the image to be appearing on the other side. So if you put a screen here, you can get the image projected on this point. So that's why it's a real image. You can see that the light rays have kind of flipped to the other direction, and that's why the arrow is pointing downwards. So it's inverted. And in terms of the size, comparing the size to the original object, yes, it's a diminished image. Now, one thing you need to know about converging lenses is that when you place the object at different distances from the lens, you get very different image characteristics. If you have a magnifying glass or a convex lens at home, do try and take a look, and you'll find that yes, by looking at different distances, the images that you see through the lens appears to have different characteristics. So in the next few slides, we're going to look at the different image characteristics formed when the objects are placed at different distances from the lens. So we started off with object that is very far away. Let's bring it a little bit closer. And this time the object is still quite far away, but it's more than 2f. That means more than double the focal length of the convex lens. So on this slide, I've marked here f and 2f, where f are the focal points, while 2f is at a point double the focal length from the middle of the convex lens. So first of all, let's go through how to draw the ray diagram, and from there, we will determine the image characteristics. So every time we want to draw the ray diagram, remember that we need to draw a minimum of 2 light rays. We draw them from the top of the object because if we start from the top of the object, then the light rays will show us where the top of the image would be. So remember earlier, we learned about the 3 different light rays, and I told you you only need to draw 2. We will be drawing ray path number 1 and number 3. So the first ray path is a light ray that is parallel to the principal axis. So you start from the top of the object all the way to the center of the lens. You must draw the arrow to show that this is the incident ray. Any light ray that's parallel to the principal axis will always travel through the focal point or the principal focus. So from here, we draw a light ray that starts from this point and it goes through the principal focus or the focus point. Now, the second light ray that I recommend you draw is a light ray that goes through the optical center. So start from the same point on the object and draw a light ray that goes all the way through the optical center to the other side. The image is formed at the intersection point of these 2 rays. Why these 2 rays? Because these are the 2 light rays that have refracted through the convex lens. So the intersection of these refracted rays will form the image, and this intersection point here is where the image is formed. So you must start these 2 light rays from the same point on the object so that you can get the point of the image. That means this point is the image formed of this point on the object. So if both points start from the same point on the object, then the intersection point of these refracted rays will be the top of the image. However, you can see that this intersection point is formed below the principal axis, which means that the image is pointing upside down like this. So the object started from the principal axis upwards, so the image needs to start from the principal axis to this intersection point. So this is the image. Remember that when you draw the light rays, you must draw the arrows before and after the convex lens. So now that we have the image formed, let's determine the image characteristics. The image characteristics are obtained by comparing the image against the original object. So you can see that the image is formed on the other side of the lens, meaning it's real, it's upside down, so it's inverted, and the size is smaller than the object. If you're wondering how do we compare the size, you literally compare the size against the object. It means you can take your ruler, you measure the height of this image, compare it against the height of the object. And if you measure this, you will find it is smaller. That's why the image characteristics are real, inverted, diminished. Based on this diagram, we find that the image is formed between f and 2f. In addition to knowing the image characteristics, it is also good to know what kind of application could be used in this situation. Meaning, if we use this biconvex lens in a device, what use would we get for an image that is real, inverted, diminished? The application is a camera lens. That means if you imagine this is the camera lens, this is the object, you're taking a picture of somebody. If it's a film camera, that means the film needs to be placed over here and the image will be projected onto the film to get a clear image. If you're not using a film camera, if you're using a digital camera like in your phone, then this is where the sensor should be to pick up the image and then transform it into a digital form. Obviously, you need a diminished image because your camera is so small but actual object is so big. So that's why you need to get a real image that can be projected and diminished. You will get an inverted image, but if you use a digital camera, the software will bring it to the right way up. Now, let's bring the object closer and place it at 2f. Again, to draw the ray diagram, just draw the same two light rays. The first light ray is parallel to the principal axis and it goes through f, and the second light ray goes straight through the optical center. Again, remember that both these light rays need to start from the same point on the object, and you should start from the top of the object so that you can get the top of the image. And if you draw this correctly, you will find the intersection point of these two refracted rays formed here, and it happens to be exactly where 2f is. So this is where the image is formed. And if we compare the image against the object to get the image characteristics, you will find that the image is real, meaning it can be projected on the screen and be very clear if the screen is placed here. It is upside down, meaning it's inverted, and if you measure the size of the image, it is exactly the same size as the object. And yes, the image is formed at 2f, at equal distance away from the object. Now, what use would we have for a situation where we get a real inverted same size image? This is very useful when we're using a photocopier to get equal size copies. So we get a real image to get a copy of the document, and we want the document to be the same size as the original. Again, it will be inverted, but you just need to take your paper and flip it to get the right way up. Now, let's bring the object even closer and place it between f and 2f. We'll draw the same two light rays again. The first light ray is parallel to the principal axis and it goes through the principal focus or focus point. The second light ray starts from the same point on the object and travels straight through the optical center. And you can see now the image is formed on this side. So this is where the image is formed. And if you compare the image against the object, you'll find that it is real because it's projected on the other side of the lens, and it's upside down, meaning it's inverted. So we get a real inverted magnified image where the image is formed at a position that's more than 2f. So in what situation would we want to get a real inverted magnified image? So this would be great for a projector. That means your projector projects the image onto a much larger screen compared to the original. So even if you're using a slide projector, which is really old and that doesn't really exist anymore, but back then we used tiny little slides, but the image formed is very big on the wall. Now if you're wondering, do we really want an inverted image? This inverted image can't be helped because that's how the image is formed. So normally in that situation, we will have to put the slide upside down to begin with, so that when we see the image formed on the screen, it is the right way up. Moving on. Now we place the object even closer by placing it at f, meaning we place it at the principal focus or the focus point. Again, we draw the same two light rays. one light ray parallel to the principal axis, and then it goes through the principal focus or focus point. And the second light ray starts from the same point on the object and goes through the optical center of the lens. Now, if you do this correctly, you will find that there is no intersection point or convergence point between these two light rays. And mathematically, they should make sense. Because your object is placed at f, that means the distance of the object from the center of the lens is the focal length. When you look at what's happening on this light ray path, it's also an equal distance. The distance from here to here is also the focal length. So this distance is equal to this distance. That's why we end up getting a pair of refracted rays that are parallel. So this means that we cannot get an image formed because there's no intersection point. So no matter how you extend the light rays, whether you go forward or backwards, they're parallel. So how we describe this is that image is formed at infinity. So remember that when it comes to lenses or ray diagrams, the term infinity here means very far away. Or in other words, you can say no image formed. Is there a use for a lens with the object placed at this position? Actually, yes. It's to produce a parallel beam of light. So that means that the object that we place here could be a light bulb. So the light rays that travel from the light bulb towards this lens would come out parallel. So this is really good for things like car headlights or spotlight for a stage to get a parallel beam of light. Now, let's place the object even closer at a position that is less than the focal length of the lens. So we'll draw the same two light ray paths again. One light ray path parallel to the principal axis, and it goes through the principal focus or focus point. The second light ray starts from the same position on the object and goes straight through the optical center. Now in this case, you'll also find that, hey, the refracted light rays don't have an intersection point here. They do not converge on this side. Does that mean that there's no image, just like on the previous slide? No, because although they're not converging here, but you can see that they are diverging, which means that you can get an intersection point, just not on this side. We need to extend the light rays backwards. So how do we extend the light rays? We place our ruler in line with this refracted ray path and extend the line backwards like this. Now, whenever you extend a line backwards, you should draw them in dotted lines. Why? Because this is a guideline. We draw solid lines to represent the actual ray paths. That means this is actually how the light rays would be traveling. But because we're extending this backward, when we extend the light rays backwards, the light rays are not actually traveling along this path. So that's why we draw the line as a dotted line. So now we're going to do the same thing for the second light ray. We're going to extend it backwards. So the intersection point is formed here, which means that the image is formed over here. Because the dotted lines make up the intersection point of the image, we need to draw the image as a dotted image. So this is the image formed. Now let me explain a little bit about the dotted image. So remember, every time at least one of the lines that make up the intersection point for the image is dotted, you should draw the image as a dotted image. The reason why it's dotted is because it is a virtual image. So remember that a virtual image is an image that cannot be projected on a screen. In the earlier slides, we drew the images with a solid line because they're real. Real images can be projected on a screen, meaning you're getting a copy of the original object. Virtual images, however, can only be seen, but they cannot be projected. So it's kind of like they're there, but not really. Like they're not real. So that's why we call them virtual, and that's why virtual images are drawn as a dotted image, because they're not really there. So comparing the image against the object, we find the image characteristics are virtual, they're upright because they're both pointing upwards, and the image size is bigger than the object. That's why it's a magnified image. So you get a virtual, upright, magnified image. One thing to note, virtual images are always formed on the same side as the object, or in other words, the image is formed behind the lens, and in this case, the image is formed behind the object. What would be a good use of a virtual upright magnified image? using the lens as a magnifying glass. Because obviously, if we're using a magnifying glass, we want to magnify the image. So if you're looking at a very small object, or if you're trying to read very small words, we want a magnified image that is upright so it doesn't confuse us. They're both pointing in the same direction. So that's why when we use a magnifying glass, we normally place a magnifying glass very close to the object so that we can get a virtual, upright, magnified image. So based on all the slides, you can see that for a converging lens or a convex lens, when the object is placed at different positions from the lens, you get different image characteristics. Are you expected to know all the different image characteristics as well as the applications for the different object positions? Yes, you're expected to know them. Now, so we're going to look at a summary of the convex lens shortly, but let's go into the diverging lens first, which is the concave lens. So similar to the converging lens, there are also different types of diverging lens. So a concave lens is a lens where the curvature of the surface, it goes into the middle of the lens. So a concave lens basically is a lens that curves on both sides. The curvature could be equal or could be different. If the curvature on both sides of the lens is equal, it's known as a biconcave lens. So that means that the lens is symmetrical with equal curvature on both sides. A plano concave lens is a lens which is only curved on one side like this, and the other side is flat or plane. A negative meniscus lens has curvature on both sides, but they seem to be curving in the same direction. The difference is that the curvature is in such a way that the lens would cause the light rays to diverge. So you'll find that this side of the lens is curved inwards far more than this side of the lens. So similar to the converging lens, we also need to know about the light rays that travel through the diverging lens. So light rays that pass through a diverging lens will diverge, meaning they would spread out. For this video lesson, we're going to be focusing on a biconcave lens because they're easier to understand. So in this diagram, we can see three parallel light rays traveling through the diverging lens, and they diverge as if coming from the same focal point, which is behind the lens. So even though they're not focusing towards a point, they seem to be moving away from the same focus point. This point is known as the principal focus or focus point or focal point. For a biconcave lens, the light rays will behave the same whether coming in from left to right or right to left. That's why for a biconcave lens, there are two focal points, one on each side of the lens. Similar to the converging lens or convex lens, we label the focus point with a capital F, where F is the focal point or focus point or principal focus. Remember, they all mean the same thing. For a biconcave lens with equal curvature on both sides, this means that the distance of the focal point from the center of the lens is the same on both sides. So this is known as the focal length, which we label as small f. The value of the focal length is negative because the light rays travel away from the focal point. So as we saw in the previous slide, the focal point was behind where the light rays had diverged. That means when the light rays move forward, but the focal point was behind. That's why the focal length or focus length of a concave lens has a negative value, opposite to the converging lens. So the converging lens that we learned earlier focused forward, that's why it's positive. But for a diverging lens, the focus point was behind, that's why it's negative. So a concave lens also has an optical center, which is in the middle of the lens. And the line that connects the principal focus with the optical center is known as the principal axis. So similar to the converging lens, we need to learn about the three ray paths. So remember, we picked these three ray paths because we can predict exactly how they're going to travel. The ray paths that we draw are actually almost the same as the paths we learned for the converging lens. The first light ray is a light ray that is parallel to the principal axis. All light rays that travel parallel to the principal axis will diverge away from the focus point. So all we need to do is draw a light ray that is moving away from the focus point. Now you can see that part of the light ray is drawn with a dotted line. So remember what I mentioned earlier. we draw the part of the light ray where it actually travels with solid lines. That's why here it's solid, because this is where the light rays will be traveling for real. However, this is not where the light rays are traveling, but we need to show clearly that the pathway seems to originate from the focus point. Because this is a guideline or an extension of the ray path, that's why we draw this part as dotted. The light ray does not actually travel along this path. So if this is a path that a light ray would travel moving forward, then if the light ray comes in the other way, it would be the reverse. So if the light ray travels towards the focus point, it would come out parallel to the principal axis. Now, because we want to draw it from the left side, we don't aim it towards this focus point. We need to aim for the other focus point like this. Again, part of the light ray is dotted. This is solid because the light ray actually travels up to the center of the lens. Once the light ray reaches the center of the lens, it will travel parallel to the principal axis. So the light ray actually travels this way to the center of the lens and then parallel to the principal axis. So because this is only a guideline, we draw it dotted. You still need to draw this part of the path to show that the light ray is being directed towards this focus point. The third light ray that we draw is identical to the third light ray path that we drew in a converging lens. It's a light ray that is directed towards the optical center. Now, regardless of whatever lens that we use, any light ray that travels towards the optical center will continue in the same direction. So it's very easy to draw. So remember that when you draw this ray path, you must always draw the arrow. So one arrow on the light rays before and one arrow on the light rays after the lens. So these are the three ray paths you need to know that are traveling through the diverging lens. And I'm going to label this as ray path number 1, number 2, and number 3. So if we were required to draw the ray diagram for a diverging lens, again, similar to the converging lens ray diagram, we only need to draw 2, and my recommendation is to use a similar 2 ray paths. Draw ray paths number 1 and number 3. Why don't we do number 2? Because it is very confusing. So for the next few slides, I'm only going to draw ray paths number 1 and number 3. If you're very curious to know about ray path number 2, I'll cover that in another video so that you know why, but I'm not going to do this right now because it will just confuse you. So now, let's learn to draw the ray diagram for a diverging lens. So we've got an object placed on the left side of the concave lens, and because this is a biconcave lens, we have 2 principal foci or focus points at equal distance from either side of the lens. So to draw the ray diagram and to obtain the image, we're going to draw 2 ray paths, and remember, both of these ray paths need to start from the same point on the object, which is at the tip. So the first ray path is parallel to the principal axis, and you draw it up to the center of the lens. Any light ray that travels parallel to the principal axis will diverge away from the focus point for a diverging lens or concave lens. So remember, you need to draw the dotted line from the principal focus or focus point to the center of the lens and then continue with a straight solid line through. The second light ray you draw should start from the same point on the object and travels through the optical center without any change in direction. As you can see, there is already an intersection point over here. So remember what I mentioned earlier. If at least one of the lines creating the intersection point for the image is dotted, the image you draw should also be a dotted image. So this is the image formed. A dotted image means that it is a virtual image. So if we were to compare the image against the object, besides the image being virtual, they're both pointing upwards, which means that it is upright, and the size is smaller, meaning that it is diminished. So the image characteristics are virtual, upright, and diminished. And remember, virtual images are formed on the same side of the lens as the object, and we can describe this as the image is formed behind the lens. Now, the diverging lens is not the same as a converging lens. So unlike the converging lens, no matter where you place the object, the image characteristics are the same. So just to prove this to you, we're going to draw it again, but this time with the object placed closer to the lens, at a position less than f, less than the focal length of the lens. So again, we'll draw the same 2 ray paths. The first ray path is a light ray that's parallel to the principal axis and diverges away from the principal focus or focus point. The second light ray will travel through the optical center. And straight away we can see this is the intersection point, which is where the image would be formed. Again, there's a dotted line creating the intersection point, so we get a dotted image. And if we compare the image against the object, the characteristics are virtual, upright, diminished, exactly the same as on the previous slide. So wherever you place the object in comparison to the diverging lens, the characteristics of the image formed are exactly the same. So now, let's have a summary of all the different image characteristics for the object placed in front of the lenses. So for the converging lens or the convex lens, different object positions will give you different image characteristics. And as I said earlier, you are required to know this. So U is the object distance, meaning the distance of the object from the center of the lens, while F refers to the focal length. When U is placed at a distance greater than 2F, the image characteristic is real, inverted, diminished. When U is placed exactly at 2F, you get an image that is real, inverted, and same size. So when U is placed exactly at F, the image is formed at infinity, or you can say no image formed. And when U is placed at less than F, you get a virtual upright magnified image. For a diverging lens or concave lens, all images formed are virtual, upright, and diminished. Now before we move on, let's just look at the image characteristics. If you feel this is quite overwhelming, let's just look at some patterns to help you remember. One of the important things that you must take note is that a real image is always inverted. As you can see, it's always real inverted, real inverted, real inverted. Whereas virtual is always upright. Virtual upright, virtual upright. You can see there's no real upright or virtual inverted. This is true when you use a single lens. If you have an optical device that uses more than one lens, it's possible to mix them up, real upright and virtual inverted. But if it's a single lens, as you can see from this slide, real is always paired with inverted, while virtual is always paired with upright. Now in terms of the size, the sizes are not random. You can see that when the object is placed far away, it's actually diminished, and as the object gets closer and closer to the lens, the size of the image is increasing from diminished to same size to magnified. So that's another way that can help you remember the characteristics. And for same size as only one position, it's exactly when U equals to 2F. So it's diminished here, and as it gets closer, it becomes same size and then magnified. Just remember that beyond F, you get real inverted, and when it's much closer, you get virtual upright. At 2F, you get same size, so beyond that, it's diminished, and closer than that, it's magnified. For diverging, very easy, virtual upright diminished. So one of the ways you can remember this is to remember very ugly donkey, VUD. So for a diverging lens, you have a very ugly donkey, virtual upright diminished. Now this donkey is very cute, but I couldn't find an image of an ugly donkey, and I don't think you want to see one anyway. So here's a diagram I created which might help some of you remember this. So for a convex lens, if the object is placed at a position less than F, you get a virtual upright image, while if it's beyond F, you get real inverted. If the image is placed exactly at 2F, you get a size that is the same, while more than 2F is diminished and closer than 2F is magnified. So how you could use this is to see where the overlaps are. If the object is placed more than 2F, you get real inverted diminished. Placed at 2F, real inverted same size. Placed between F and 2F, real inverted magnified. At F, there is no image. And less than F, you get virtual upright magnified. Also, just a reminder that you do need to know of the applications, and we're going back to this table. So how to remember the applications? Remember to look at the image characteristics and understand which image characteristic would be useful in that particular optical device. So I've already explained these applications earlier, so I'm not going to re-explain this. This table is just a summary for you to refer to. Now besides these, there are also other applications of converging lenses that you should be aware about. These are the uses of applications using a single lens. Sometimes we could be using optical devices that uses two convex lenses. For example, a compound microscope and a telescope. There are two lenses, one placed at the eyepiece and one at the objective lens here. And for the telescope, the same thing. There's a lens here at where we place the eye, known as the eyepiece. And the lens on the other side is known as the objective lens. Now, I'm not going to go through the microscope and telescope in this video lesson because the explanation for the compound microscope and telescope will be quite long and not all syllabi cover this. So if you'd like to learn more about a compound microscope and telescope, I will cover that in another video. For now, we're going to move on. Now, so far, we've only been learning about the applications and uses of converging lenses. We haven't gone through any of the applications of a diverging lens or a concave lens yet. Now, just to let you know, a diverging lens or a concave lens is very rarely used in an optical device. Why? Because the image formed is virtual, upright, and diminished. So virtual images cannot be projected on the screen, so which means you can't get a copy of it, and you get a smaller image. So what use is there for a virtual diminished image? You can't think of any, right? Does that mean there's no use for a diverging lens? Well, actually, there is a use, and it's about correcting eyesight. So both the converging lens and diverging lenses are used to correct vision. Let's look at this diagram first. So this is a diagram to show how a light ray should be traveling into our eyeball. So here's the eye lens and here's the retina, and you should know that the lens in our eyes are convex lenses. So when the light ray enters our eyes, it will refract through the lens and they will converge onto the point of focus, which is where the retina is, and our optical nerves will pick up on these light rays and send the data to our brain to interpret the image. So in order to see a clear image, the light rays need to be focused towards the retina. However, as we know, not everyone has perfect eyesight. So some people may suffer from long-sightedness. So long-sightedness means that you can see objects far away clearly. So near objects, they can't see clearly. So the reason for the long-sightedness is because the light rays that refract through the lens end up focusing behind the retina. So because they're not focused towards the retina, the image is not clear. How to correct this? This person would need to wear glasses with converging lens. So by wearing a converging lens or a convex lens, before the light rays reaches the eye lens, they'll pass through this convex lens and they'll be focused. So that means the light rays have been brought closer, and then they will refract again through the eye lens. So the convex lens helps to bring these light rays to be focused at a closer distance from the original so that they can focus at the retina. People who are short-sighted can only see near objects clearly. That means that objects that are far away can't be seen clearly. So short-sightedness, short distance, they can see more clearly. So people who are short-sighted have the opposite problem of people with long-sightedness. The light rays this time are focused in front of the retina. So you can see now they're focused in front of the retina. So people who are short-sighted need to wear glasses with diverging lenses or concave lenses. So what happens is the light rays will diverge with the diverging lens first, so they spread out before being refracted again through the eye lens. So by spreading out the light rays, this helps to bring this focus further back so that they can focus directly onto the retina like so. So you need to know which lens is used to correct which type of vision issues. So converging lenses are used to correct long-sightedness, while diverging lenses are used to correct short-sightedness. So before we end this lesson, one more time just to remind you about the ray diagrams. All the light rays must be drawn to the center of the lens. Remember, the center of the lens we are referring to here is this dotted line, which is marking where the center of the lens is. So the light rays that you draw parallel to the principal axis must go to the center of the lens and then goes through F, whereas a light ray that goes to the optical center, just draw a line straight through. So this is true for all lenses and all object positions. So even in this case, remember, parallel to the principal axis to the center and then goes through F. This line is a straight line through, and this is true also for diverging lenses, straight to the center of the lens and then away from F, and the second light ray is through the optical center. And that is it for this video. So if you found this video to be educational and helpful, do click like and comment on how you found this video to have helped you. If you would like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page, that's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do check out my videos on my YouTube channel on other topics you might find helpful. Subscribe to my YouTube channel for more free physics lessons from your physics teacher, Miss Ho. Happy studying!